is not given, but the circuit description is given. And then, so I want that. So again, I'll repeat that thing, that the strategy or the steps for the bridge based problem. First of all, you draw. If it is your bridge circuit is not drawn, you draw the bridge circuit from the circuit description in the problem, and then you derive the balance equation, and then you calculate the value from the balance equation. So I want that all of you should draw the diagram, and then you derive the balance equation, and then you solve. One more thing I want to, because you see in Hayes bridge, there are, means if your your quality factor of the coil is high, more than 10, then you can use this simplified expression. And for R1 also, your expression will get simplified. Here your this term will become, means your denominator will become 1, because if it is quality factor of the coil is more than 10, then this will become less than 1 by 100, and obviously this term will be negligible. So only you will have omega square C4 square R2 R3 R4 as far as R1 is concerned. As far as L1 is concerned, for high Q coil, means quality factor of the coil is more than 10, then R2 R3 and C4, L1 is equal to R2, your denominator will be equal to unity. So this is how your balance equation will also get simplified if we are having a high Q coil. So now in this problem, I want that first of all, after drawing the bridge diagram, and deriving the balance equation, you should whether we can have a approximate balance equation or exact balance equation. So this will be decided by the quality factor of the by calculating the quality factor of the coil. So I want that first of all you should calculate the quality factor of the coil. Then you decide whether you will use the approximate balance equation, or if your quality factor of the given coil is more than 10, then we can go for the approximate balance equation. If you are having any query, you can ask, please. We solve this example. You solve quickly, please. If you are having any problem in any step, then you can ask. I'll take your attendance. रोल नंबर 1, इसको सॉल्व करने में कोई इशू आ रहा है तो बता दें हमें.
No,
Then tell me the answer.
sir, quality factor 14.107.
14.10. So you must have calculated with the 1 upon omega 4 C4. Okay.
Yes, sir.
1 upon omega R4 C4. So since it is more than 10, then you can use approximate formula like balance equation for L1 is equal to R2 into R3 into C4, and L1 R1 is equal to omega square C4 square R2 R3 R4. Now you calculate these values. This is the equation. Although I had calculated it through the exact equation, but if quality factor is more than um, quality factor as you calculated, someone is calculated, it is coming out to be Q is equal to कितनी आ रही है भाई?
107.
14.107. So 14 point 107. So obviously we can calculate L1. You can compare also if you are calculating with the exact equation. So L1 you can use R2 R3 into C4, sorry. So with this equation you can, similarly you can use approximate equation for. So yes, can anybody tell me the calculated value if you have done?
0.6326.
1
Sir, 0.6326.
0.6326. So you can see that 0.63 जो है, from exact equation we are getting this. And R1 how much you are getting?
R1 का भी नहीं देखा.
Right. Because the frequency is given here 500 hertz. Okay, because in calculation of R1 you require frequency also, value of the frequency, because it is a omega square, C4 square, R2, R3, R4. Anyway, you should calculate it. I'm moving ahead. Now another bridge, it is called Owen's bridge. Owen's bridge is also used for measurement of um, inductance in terms of the capacitance. So this is the bridge circuit, and this is your unknown coil. These are the other components. These are basically the known bridge arm components. And when the bridge by here you can see that R2 and C2 are the variable components. And again I'm telling you just to remind you that if your um, variable components are in same arm, then resultant balance equation will be independent. So that's what that has been taken. But as I told you that earlier, that always this may not be possible. Generally the general choice or the most desirable from accuracy point of view, we always want that our resistance should be variable. Inductance and capacitance we avoid, just because of the accuracy and the cost also. So anyway, step remains same as far as the we wrote the uh, arm impedances, and then we put this arms impedances into the equation, into the balance equation. And then finally you can see that we are getting out of this impedance balance equation, we are getting two balance equations. From one balance equation we are getting value of inductance, unknown inductance, or from another we are getting unknown resistance of the coil. And again, this Owens bridge is, as far as the advantage of Owens bridge is concerned, it is uh, its balance equations are simple and they are independent of frequency. And if we are choosing R2 C2 as a variable components, then your balance equations are also independent, so there will not be the sliding balance problem. And disadvantage or limitation I discussed, that bridge requires a variable capacitance which is expensive, and also its accuracy is about 1%. So that's why as I told you that if variable capacitance and inductance we are using, their accuracy is not means if very accurate result you want, won't get accuracy as good as the variable resistance. So that's why. And then here also, this is having a same kind of limitation, this bridge, as the Maxwell's bridge was having. Here, if your coil Q, quality factor of the coil Q, quality factor of the unknown coil is high, then you require very high value of resistance R2. So that is the issue which your Owens bridge has. So that's why. Um, so this is the limitation of Owens bridge. Now this is the problem related to the. So anybody is having, if having any question regarding Owens bridge, you can ask. Yes, please. Its derivation is also simple, unlike your Hayes bridge, and balance equations are also simple. So if anybody is having any query regarding anything which we have discussed about this bridge, you can ask, please. Otherwise, you solve this problem. You are required to calculate the impedance of the specimen. You see, here in this problem, you can see that sheet steel, instead of coil, we are using sheet steel. So electrical methods are used for quality control also. Like in this case, you see, we are using Owens bridge to test the sheet steel. Basically, the quality of the sheet steel can be assessed in where it is manufactured by using this electrical testing method. So when your sheet is perfect, is not having any imperfection, manufacturer defect, manufacturing defect or imperfection, then it will have a certain value of impedance. Now if any sheet steel is having during manufacturing some defect is there, so when you will measure the impedance of the sheet steel, then its value will be different from whatever a good sheet steel will have. So this way, means the procedure is very simple. What they do, they take a good sheet steel, and here they connect a good sheet steel, and they vary the variable component, and they balance the bridge. Now once your bridge is balanced for the uh, good sheet steel, now they bring the specimen, they connect here, and whenever it becomes unbalanced, because when your sheet steel is not having that impedance value which a good sheet steel will have, good quality sheet steel will have, then this bridge will become unbalanced because that impedance will not be the same. And so this is one of the way that quality control is done using electrical testing methods. This is widespread. So this is what is the application. Anyway, you solve the problem. I just describe you the application. Okay. By the time you solve this problem, I'll take another set of attendance of another set of people. Now roll number 31,
Present, sir.
32,
Yes, sir, present.
56, roll number 56, 57 inductance.
Inductance 0.834 Henry.
Now calculate the impedance if your frequency is 2 kilohertz. This frequency is given. क्या वैल्यू आई इम्पीडेंस की? ओम्स में वैल्यू चाहिए मुझे बस। भाई इंडक्टेंस और रेजिस्टेंस की वैल्यू मालूम हो गई तो इम्पीडेंस में क्या इशू है? इंडक्टिव रिएक्टेंस कैलकुलेट कर लीजिए और फिर एम्पलीट्यूड हमें बता दीजिए। अंडर रूट आर स्क्वायर प्लस एक्स स्क्वायर। कितना बताया था आपने इंडक्टेंस?
0.834 हेनरी।
8.34 मिली हेनरी आ रहा है। 0.00834, चेक इट है। और
Yes.
रेजिस्टेंस 80.64 ओम and your impedance is coming out to be 132.23 ohm। ठीक है, चलिए ये कैलकुलेट कर लीजिएगा। Now this is another bridge, Anderson bridge, and this bridge is considered as one of the means it satisfies means with this considered as the best bridge for measurement of inductance. Few attributes at the onset I'll try to explain you that the you can see that these two resistances are taken as the variable resistance. So in this case, you see, we in other bridges, whether it is a Maxwell's bridge or it is a Hayes bridge or it is a Owens bridge, in all these bridges that we have discussed till now, in those bridges, inductance or capacitance are taken as a variable component. And if we are not taking inductance and or capacitance as a variable component, then there is a problem of sliding balance if we are choosing any other component. So but here you can see that um, uh, we are using two variable resistances to balance the bridge. So but this bridge is little bit complex. It's not as simple as other four arm bridge. It is basically a five arm bridge. This is one more arm. It is considered as a one more arm. So it is different from the four arm bridges, but it offers many advantages. And one of the advantage I discussed just now, that other advantages are also there, and you have to keep that. So only disadvantage with this bridge is that its circuit is complex. It is having more nodes, so the shielding and all require means this makes difficult shielding. It will make shielding difficult and all. So anyway, so we'll discuss this now. To what I have done to analyze this bridge and to derive the balance equation, I tried to simplify it. So what I have done, I converted, if you can look upon this part. So this is your basically this part, the R2, R4 and small r. This part is basically making a star. So I converted into delta. So this is your star and I converted it into delta. So additional your delta converted resistance R4, R6 and R7. And this is the formula, R5 is equal to this multiplication of this R into R4, R4 into R2, R2 into R4 divided by the farthest one, R4. Like this. Similarly, R6 will be divided, same thing will be divided by R2, and in this case R7 divided by small r. So this way. So I want that you people draw the transformed circuit. What will be the transformed circuit? I want answer from you. After conversion, you connect this delta here and then tell me what is the, is there any simplification or anything? What is the outcome? That's what I want. Whether it is simple or it is more complex. Draw it, please. Anyway, this is the transformed. This was your original circuit, Anderson bridge original circuit, and this is your transform. You see that your R5 and R6 is coming here. R5 and R6 is coming here. So this is your basically delta. This is your delta. So if you look upon this bridge, you see it is basically, if you look these two arms and these two arms, these are basically the 5 arm bridge is converted into 4 arm bridge, and we are more familiar and comfortable with this. And R7 is not having any role to play. This is basically appearing across the across the supply. This resistance is appearing across the supply. And if you look this, as far as this bridge is concerned, R1, L1, R3, C, R6, and R5. This is basically a Maxwell's capacitance comparison bridge. These RC and R6 is coming are in parallel. So that's what I had written. It is apparent that transformed bridge network is that of Maxwell's capacitance bridge. Or balance equation इसकी ये हो जाएगी obviously. Now we'll put the values. We'll put the values, your R5 and R5 and R6 values here. So your L1 will be this, balance equation will be this, and for your R1, this will be your balance equation. Okay. Actually, in this case, your R1 is a discrete resistance, and small R1 is basically the inductance resistance. So small R1 will be, so in this case, as you see that R1 and R is the variable. So you can see that your R1 is coming in one equation, and your small r is coming in another equation. So you see that these two equations are independent also. And so sliding balance problem will not be there. So that's why this bridge is considered as a very good bridge, because whatever is the desirable situation we are we want in a AC bridge, that this bridge is offering. Here in this case, from accuracy point of view also, this is a good bridge, because the variable components are the variable resistance. And with the choice, although we are not forced to have any inductance or capacitance, here in this case capacitance as a variable. So in this case you see that the resultant balance equations are all also independent with the choice of the variable component, although variable components are not lying in the same branch, and it is not. So this is how this Anderson bridge is offering. This is a very good bridge. It is very easy to balance also, because in this case your capacitances, your resistances are variable, and sliding balance problem is not there, because your equations are independent. So if anybody is having any question regarding the derivation of balance equation and whatever beyond that, whatever I talked about, you can ask please, as far as Anderson bridge is concerned. कोई क्वेश्चन नहीं है आपका?
सर जो मैक्सवेल कैपेसिटेंस ब्रिज में एक और प्रॉब्लम थी, वो लो R4 की वैल्यू के लिए जब ज्यादा लो हो जा रहा, तो वो भी इसमें खत्म हो जाएगी।
या वो इशू नहीं है इसमें, क्योंकि आपका एक्चुअल ब्रिज तो ये है ना, ये तो ट्रांसफॉर्म होने के बाद हुआ है ये। Your actual balance equations are these. These are the, because here you can see that your actual bridge components are in terms of actual bridge components. So this bridge is good for for a wide range of, as far as the Q factor is concerned, for wide range, from very low range as well as very high Q factor. I had discussed it here. In case adjustment are carried out by manipulating control R1 and R, they become independent of each other. Means that's what I told you. This is a marked superiority over the sliding balance condition met with the low Q coil. So you can say that, because you see, in case of Maxwell's bridge is not good for the low Q coil also, because of the issue here. Here you see, since normally fixed capacitance is used and balance is obtained by manipulating R2 and R4 alternatively. So when you are making R2 and R4 as a variable, then sliding balance problem will occur, and for the low Q coil, this sliding balance problem will be more pronounced. So the for low Q coil, with the choice of, with R, with the R2 R4 as a variable, it is very difficult to balance the bridge because of the sliding. That issue we are not having in Anderson bridge. So Anderson bridge is good for the low Q coil, quality factor coils also. It is easy to balance, and overall also it is easy to balance. So that's what it is written. This is a mark superiority over the sliding balance condition met with the low coils when the measuring with the Maxwell's bridge. A study of convergence condition would reveal that it is much easier to obtain balance in case of Anderson bridge than in Maxwell bridge for low Q coil. And unlike Maxwell bridge, it uses a fixed capacitance, so it is not using, so cost wise also it is economical. Now you solve this problem. You see, this is the problem based upon the Anderson bridge, and again I will tell you that this is one of the format. In this case, you are required to draw the bridge. Every case, in all the cases, you are required. So here you can identify that nodes are more than four: A, B, C, D, E. Here E. So you can from here you can find out, means you can identify that this is Anderson bridge. So again, you are required to draw the circuit diagram and derive the balance equation and then calculate the values. This is the standard procedure. So in this case, although here I just put the values and then I calculated it, but in examination, again I will, even if you remember the balance equations for a particular bridge, because sometime in problem some small variation is also possible. So if there is a small variation in the bridge, then you may get confused, because your balance equation will be different. And so I so if anybody is having any question regarding Anderson bridge, you can ask, please. So this way, we finished our discussion on inductance measurement bridges. There are more bridges also. I'm telling you, if you will go to the book or literature, you'll find some more bridges also are there for measurement of inductance. So, but in your course, only these many bridges are there. But with the knowledge of these bridges, you can analyze and you can understand, you can derive the balance equation for any bridge which are used for measurement of inductance. So here, I'll summarize. So we discussed yeah, Maxwell's capacitance inductance comparison bridge, Maxwell's capacitance comparison bridge, then Hayes bridge, and then Owens bridge, and then Anderson bridge. So these bridges are used for measurement of inductance. So the Maxwell's bridge is used for medium resistance, medium Q coil measurement, and Hayes bridge is suitable for high Q coil, and Anderson bridge is suitable for. Although Anderson bridge is good for wide range of the quality factor coils, but it is good for, especially other bridges are not good for the low Q coil. Anderson bridge is good for the low Q coil. So this is what we discussed. We derived the expression, balance equations, and then we solved the numerical problem. So if anybody is having any query regarding any of these bridges which we have studied, you can ask. Anyway, if you don't have any question, then we'll move to the part of. Now I'll discuss the measurement of um, capacitance. There are set of bridges which are used for measurement of capacitance. So now we'll discuss the measurement of capacitance. The way we discuss means there are set of bridges for measurement of inductance. There are set of bridges for measurement of capacitance also. So now these topics or these bridges will discuss in measurement of capacitance. So I'm starting with the D Shorty's bridge. The Shorty's bridge, you can see that it is considered as one of the simplest AC bridges. And in this case, you look upon it and you see the derivation. You will find there is only one balance equation. Yeah, it is not like other, because its circuit is so simple that. So here in this case, this is your C1 is your basically unknown capacitance, and we want to know the value of unknown capacitance. So when the bridge is balanced, then it will satisfy the balance equation, and this is the formula from the balance equation. We got the value of C1 in terms of the known other bridge components, bridge arm components. So you look upon it and you see that how simple is D Shorty's bridge. So obviously it is having a single balance equation, so there will not be any sliding balance problem here, and only one variable component is required to obtain the balance, because you have to satisfy only one balance equation. So because of all these, this bridge is considered as a simplest AC bridge. Now there is one great limitation of this bridge. Can anybody tell me what is that disadvantage or limitation? Limitation, I'll say limitation. It is this bridge is for the lossless capacitance. Means if your capacitances are, your unknown capacitance is lossless and your known capacitance is also lossless, only then your bridge will be balanced. Otherwise your bridge will not be balanced. So this is not for the lossy capacitance. If your capacitance is lossy, then this bridge will, you cannot use this bridge, and it is not difficult to balance the bridge. So it is basically for lossless capacitance. This is one of the severe limitation of this bridge. So that's what I had written. The balance can be obtained by varying R3 or R4. The advantage of this bridge is its simplicity, but this advantage is nullified by the fact that it is impossible to obtain balance if both the capacitors are not free from dielectric loss. If they are they are lossless, only then this bridge you can balance. Thus with their method, only lossless capacitor like air capacitors can be compared. So this is what is the disadvantage of D shortage, limitation of D shortage. And for to overcome this disadvantage, modified D shortage bridge is used, where the you can have a ideal capacitance, or you can have lossless or lossy, or both the capacitance. So anyway, I'm stopping my today's discussion here only, and here in this case, So if anybody is having any question regarding de-Torsades bridge, you can ask, please.
Sir, other than ideal capacitor,
Lossy
capacitor.
and lossless. You talked about in lossy and lossless capacitance. So this
Actually,
is
sir, a lossless capacitor will be an ideal case. But sir, in practical ways, we will never get lossless capacitor. So it will be never used.
it's not never means you can have a like air capacitances where the air is used as a dielectric, so you can consider them as a lossless capacitor. They are very good capacitances. So it is not like that you cannot have lossless. We generally want that your capacitance should have minimum losses. So this bridge is good when your capacitor is lossless capacitor, means your balance is obtained. If it is lossy capacitance, you won't be able to balance it.
So sir, this lossy will be defined in which terms, sir?
आप बताइए लॉसेस जो है इलेक्ट्रिकल इंजीनियरिंग में किस टर्म्स में हम डिफाइन करते हैं?
So actually, sir, you told us about air. If we use air, there is also a loss. So sir, you talked about if we use air, there will be this will be lossless, sir.
Air capacitance I'm saying, air where dielectric is air. So I'm talking about the electrical engineering circuit in terms of circuit. How do you by circuit component means in terms of what we describe the loss. Loss is always power loss. Okay, and
Okay, sir, okay.
I think you must have studied lossy capacitance equivalent circuit in your circuit subject. So power loss is also always represented by resistance, I square R loss. So we are having either a resistance in series with the capacitance as a equivalent lossy capacitance equivalent circuit, or a resistance in parallel with the capacitance. These two are the, if you don't remember, you revise your circuit book, you'll find that equivalent circuit for lossy capacitance is either resistance in series with capacitance or resistance parallel with the capacitance.
Okay, sir, okay. Thank you.
Okay. So I'm stopping my today's discussion here. Next week you are having your sessional test. So as far as the sessional test is concerned, it will be conducted on the classroom, and and um, uh, your syllabus will be your complete first unit, and in second unit your inductance measurement bridges and your de-Torsades bridge, means more specifically Maxwell's bridges. In second unit, these topics will be in your course: Maxwell's bridges, then Hayes bridge, then your Owens bridge, and then um, your Anderson bridge, and finally, so whatever I taught in the second unit, that will be in your course, and then first whole first unit will be in your course. Any question regarding your syllabus and all?
No.
कोई क्वेश्चन है आपको? Okay, respond your roll call now.